Good afternoon, everyone, and welcome to the Lundin Snider seminar series. And before introducing our invited speakers, I would like to say a few words. The first thing is why having this seminar series is because our society is facing a major energy transition where mineral resources play and certainly will play a major role. However, there are general questions related to this major societal challenge, such as, can we find new mineral resources? Do we have enough? How to minimize the impact of mining on the environment and surrounding communities? How to mine responsibly while achieving this transition? And many other questions. And I think that all these questions are actually equally relevant and important and involve different players. Therefore, the goal of this seminar series is to communicate about the various aspects of the mineral resources life cycle, open ground for constructive discussions, and get a better understanding of what is at stake. The seminar series will be a monthly seminar and will consist of 7 presentations / 7 speakers. And I hope it will continue next year and the year after and so on. I won't go into details, but I invite you to look at the webpage if you want to know what are the next presentations. Also, would like to acknowledge a few people, especially Jody Banta and Mark Barton for making this event possible, and also Sharon Arsenault, Natalia Perez Rojas, Didi Duplessis, and Kaylin Burant, without whom we would not have a webpage, neither flyers or catering ready today. So don't forget the refreshments after the talk. And you also might wonder, what is the Lundin Snider name? And actually, we decided to name the seminar series to honor the Lundin family and Timothy Snider for their leaderships and gift, which have been instrumental in the development of the Lower Institute for Mineral Resources and the creation of the new School of Mining and Mineral Resources. So that said, thank you all for coming today. And it's my pleasure to introduce our guest speaker today. Sorry, I will put the presentation. And so it's my pleasure to introduce Professor Adam Simon, who is coming straight from University of Michigan, where he is the Arthur F. Thurno Professor of Earth and Environmental Sciences. He earned degrees in geology and geochemistry from the University of Maryland and Stony Brook University, and was a postdoctoral fellow at the Johns Hopkins University. His research program combines field, analytical, and experimental work to unravel the genesis of mineral systems, including iron oxide copper-gold systems, porphyry copper systems, kaolin gold systems, among others. Put it simply, Professor Adam Simon focuses on the global flow of energy and mineral resources with an emphasis on the geological availability of critical metals. Adam has co-authored two textbooks, Mineral Resources, Economics and Environment, and another one called Earth Materials, Components of a Diverse Planet. And he has published over 60 papers in the field of energy and mineral resources. And that said, I think it's all yours.
That almost makes me sound like I've done something good. All right. That's loud for me. Is it loud for you all? Or is it right on? Perfect? Okay. So I will go ahead and tell you that I'm schizophrenic, and I do really enjoy talking about this topic. I am happy to provide the slides to anybody who wants them, and I know the talk is being recorded, so you can watch this 2 or 3 times if you really enjoy it. I'm not going to talk in detail about how mineral deposits form. I want to send you away from here with only a few important messages, which are, we can transition from a fossil fuel-based energy infrastructure to one that is completely dependent on renewable energy resources. And in order to do that, and paying heed to environmental justice, we have to significantly increase metal production across the board. That's what I want you to leave with. And I'm going to start, hold on. So I teach a big natural resources class at Michigan once a year, and it's gotten to be pretty popular. And the first lecture, maybe I have to stand close, okay. So the first lecture I talk about the Bible. And right away, I can read the room, 150 students, because I can tell who's comfortable being religious, and I can tell who bristles when they see me refer to the Bible. But what I try and tell the students, and I'll communicate to you, is if you take the Bible simply as an historical narrative that describes the evolution of humans over a certain period of time in one part of the world, the connection between the Bible and resources are the 7 metals of antiquity that are shown here on the screen. So in the Old Testament describes gold, copper, silver, tin, lead, iron, mercury, and you've all now read in the book of Job how these metals are discussed. So we've known about these metals for a really long time. When we transitioned from the Stone Age to the Copper Age, wasn't because we ran out of stones. When we transitioned from the Copper Age to the Bronze Age, we didn't run out of copper. Same thing when we transitioned to the Iron Age, and the same thing today. So when you read the Old Testament as simply historical text, right, you can look at the individual books in the Old Testament, and you can correlate them up top to major periods of change for human civilization, specifically here in the Middle East. Right? If you travel to the Middle East, you can go to King Solomon's mines. You can actually physically go to this part of southern Israel, and you can stand and you can see the actual entry points where King Solomon's group was mining copper beneath the surface. It's fantastic. It's history. When you look at maps of the ancient world, right, maps exist to tell us how to get from A to B, and they exist because we find something somewhere that is valuable because of that something somewhere. So this is a map of copper production in the 2nd millennium BCE in Persia. And if you look at all of the numbers, those numbers were put on the map by ancient Persians because that's where the ancient Persians found and produced copper. When we look at the Bronze Age, that is among the earliest events where humans figured out what we now think of as chemistry or metallurgy, where they realized that if you take a metal such as copper and you add it to a metal such as tin at a ratio of about 9 parts copper to 1 part tin, that lowers the temperature at which pure copper melts, so they could melt copper plus tin and pour that as an alloy that we refer to as bronze. And that took us from the Copper Age to the Bronze Age. We went from only using copper to now using copper and tin. It put tin on the map. So if you look here, these are tin deposits in the Bronze Age world. And right away, what you can see by the colors is this was a contributing factor to humans moving out from the ancient Middle East in search of these metals. When they would exhaust metals nearby, they would move further to find those metals. It drove exploration. Here's a map of ancient Mesopotamia, Anatolia, modern-day Turkey, Iran, Iraq, and again, right, if you look at each of these symbols, you can see the name, and then you can see the metals that humans found in those places and extracted and produced, put places on the map. It drove trade. So if we look here at Mesopotamian trade routes, And a real quick look at the legend, you can see trade routes for timber, stone, copper, tin, ceramics, ivory, carnelian, shells, lapis lazuli, pearls, etc., etc., etc. Right? What we're reading here in the Old Testament, and by looking at these places where ancient humans used to physically extract specific metals, we're looking at our evolution in this part of the world, which amazes me. And then we had a couple thousand years of nothing, right? So give or take from about the year 0 until only a few hundred years ago, we had gone from Stone Age to Copper Age. We crushed it, right? The Hittites figured out how to make bronze. They could defeat armies that only had copper. Everybody wanted bronze, right? Then we had a collapse of societies around the Mediterranean, which was related to invading warriors. It was also related to climate change, drove us from the Bronze Age to the Iron Age. Then we had 2,000 years of nothing, and I want to show you here the progress. Somewhere down there is a play button. You might have to help me. Somewhere. There should be a play button. Yeah, okay. All right. So here we go from the early 18th century, and I want you to simply see the periodic table come alive. Humans in the 16, 17, 18, and 1900s went from those metals of antiquity, figuring out how to make bronze, how to forge iron, and then we had a long dry spell, and starting only a few hundred years ago, we then populated our current periodic table with 92 naturally occurring elements. Right? And we tend to forget this, right? We don't look back and think of that progress as truly revolutionary. But when you look back and you think about people that figured out what is oxygen, what is tin, what is fluorine, what is chlorine, there's phenomenal growth intellectually here as we populate this periodic table to the one that we know today. When we look more recently, right, here's an example. On the left is New York, 5th Avenue, 1900. Everybody's on a horse and buggy except one vehicle. The vehicle on my screen, the vehicle I'm not going to figure out how to use this, but the vehicle right here in red is an internal combustion engine, right? This is before Ford. If you go back to 1900, in the United States and the current European Union, there were about 250,000 people that woke up and worked 6 days a week, 12 hours a day to make carriages and buggies. All right? One internal combustion engine. Look at 1913. In 13 years, we went from a New York City where everybody was horse and buggying to a New York City where everyone who could afford it were using an internal combustion engine. Now, let's connect that to other things that we don't think about. Everybody has seen horses take a shit. They shit a lot. Imagine all of those horses on 5th Avenue shitting. There's a great Seinfeld episode that you should watch when Kramer feeds a horse a big can of beans. It's classic. That created a public health nightmare. Why? Because at night, they would literally come in and scoop the poop and get rid of it. But there was always some amount of poop that when rainwater would hit it, it would pick up the viruses and bacteria that we excrete through our anal orifice, and it would take those down into the groundwater system and then percolate throughout people. And so we see in New York, in Dublin, in London, in Paris, these horrific examples of public health crises that instantaneously, when we got rid of the horses and we went to internal combustion engines, the spread of that disease effectively disappeared overnight. When we look at how we used to farm, right, you can read the text. Farming was hard. It was really hard. Right? My father was one of 4 kids who grew up on a potato farm on Long Island. None of them wanted to become farmers because it was literally backbreaking work. So if you go back to the 19th century, it would take, on average, 25 of me an entire day from dusk to dawn to harvest and thresh a ton of grain. Today, with modern combines, we do that in 6 minutes. 6 minutes. Combines are air conditioned, they have pneumatic seats, right? They're GPS controlled, you have satellite radio, you can podcast, and they effectively drive themselves. So what did this do? A number of things. It allowed us to significantly increase the quantity of food that we produce to feed a growing population, and it also resulted in the other 24 people having to find other work. So the share or the percent of Americans who worked directly in agriculture plummeted. In 1850, about 75% of all adult Americans worked directly in farming. 3 out of 4. By 1900, it was 1 out of 3. Today, it's less than 2%. Why? Because we have ideated and invented technology that effectively farms for us. How many people know a blacksmith? No, you don't. You know somebody who's wealthy enough to dabble in blacksmithing. But nobody knows real blacksmiths. There used to be hundreds of thousands of blacksmiths across the developed world. Hundreds of thousands. And then all of a sudden, the Industrial Revolution came along. We ideated our ability to mass produce tools made of steel, which effectively eliminated the need for blacksmiths. And you see this if you look at paintings and read stories at the time. Anybody who ever goes to Baltimore on the campus of the Johns Hopkins University is the Baltimore Museum of Art. And this is one of my favorite paintings. Right? It shows what happened almost overnight when all of the blacksmiths were effectively put out of work. We didn't need them anymore. When we look at technology, it should amaze you. Seriously. If you go back 600 years to the invention, the ideation of the printing press, think of what that did for religious freedom. Right? Transformed the way Europeans think about religion because it was able to mass produce and spread the Bible. So it disconnected the need to have priests as the only learned people in the community because everyone could afford the Bible. It's amazing. We don't tend to make that connection. And then if you look at the shape of the curve, everything that we use today, effectively in the last 100 to 150 years. Our lives, no matter what we think, are radically different, easier, and better than they were 100 years ago. So these are data where the left y-axis is the hours of housework per week. Not the work that you did work out of the house, but the hours of housework you had to do just to keep the house going. And if you look, if we go back 100 years, on average, 60 hours a week. Today, it's about 25. Why? Because we figured out how to harness and produce electricity on demand. That was the key. We can generate electricity on demand, and with electricity, we ideated refrigerators, we ideated freezers, we ideated microwaves, we ideated ovens, we ideated dryers, we ideated washing machines. Everything that we use today didn't exist 100 years ago. And in order to use it, we have to have electricity. And it does make our lives different, better. As a result of all of this ideation, invention, ingenuity, total economic output shot up. Right? This is the economic output in England since 1270. And what you see is, for about 400 years, not much. And then all of a sudden, you see this incredible increase in economic output. What caused it? Right? How do we back out the direct causes? Direct cause was cotton. Early in the Industrial Revolution, in the mid to late 1700s, there were a variety of new technologies that allowed for much more rapid production of raw cotton to finished clothing. As a result, what else did that do? It led to the growth of cities. At the time, most people in England and elsewhere lived in rural communities where you had to farm because it was a subsistence lifestyle. All of a sudden, we have the mass production of cotton, and you can see this when you look at the number of cotton looms over this roughly 100-year period of time. And the difference between yellow and gray is technological ideation. Humans figuring out how to use a technology device to do things better and faster and ultimately safer. As a result, here is the gross output in blue of textiles from England. And England is where it happened. Right? The Industrial Revolution started in England for a variety of factors I won't get into today, but cotton was the primary economic engine that drove the significant increase in economic output. All I want you to see here is look at the black. The black represents the number of people who truly were farmers in England in 1700, and it went off a cliff. So simultaneously, what we see is we're mass-producing textiles from raw cotton in the cities, cities that really didn't exist other than London and a very select few others. But Manchester was a nothing in 1600. Liverpool was a nothing in 1600. All right? And if you root for those teams, that's great, but they effectively were tiny little cowtown villages 400 years ago. Today, they're massive, thriving metropolitan areas. So how does this relate to resources in the United States? Well, all of that cotton came from the United States. So if we go back to the late 1700s, through 1860, the majority of cotton that was imported to England was grown and picked and exported from the United States. If you look at total economic output of the United States in toto, in the early 1800s, cotton was half of the entire export revenue for the United States. Well, what else does that connect to? It drove the slave trade. Right? What drove the slave trade? It was cotton, and then it was sugar. Why? Because in England, they had actually created by Parliament a law that disallowed importing any cotton textiles, finished products, to England. You could import raw cotton and then make the textiles in England. And so landowners in the United States and citizens of the United States who did not yet own land, they jumped on this because this represented a way of bringing in Africans to enslave as free labor to pick the cotton that could be exported, and it created phenomenal wealth. If you look at the time period 1800 to 1860, the greatest density of millionaires was in the Mississippi Valley. Why did we really want to annex Texas? Land to grow cotton. Right? There is no other explanation. And don't let anybody kid you that the Civil War was not directly about slavery. We can look at the growth of the slave population and relate it directly to resources. Took off. Why did it take off? Because England had an insatiable appetite for cotton, and people in the United States could take advantage of slave labor to produce that cotton. And you can even see the economic value of the total number of slaveries took off in parallel. Right? We literally put prices on human beings, boys and girls, men and women, who were bought and sold strictly for picking cotton that got shipped to Britain to make a select few extremely wealthy. And this is a map that shows you the density of slaves pre-Civil War. The darker the color, the higher the density. Some of these areas, if you sum the total number of slaves relative to non-slaves, slaves represented more than 75% of a given area. And cotton was the driver. So, let me jump a little bit. I made all that up on, well, I didn't make any of that up yet, but I made all that up on the plane yesterday. was telling Troy last night, a long flight across the country to LAX and then backwards, had to do something. All right? So now let's pivot. Since 1900, global population has gone from give or take 2 billion, now we're pushing 8 billion. Global gross domestic product has increased in parallel. Now, gross domestic product, typically abbreviated as GDP, it's an imperfect way of measuring economic output, but it is widely used because it can be easily determined, on average. What else increased in parallel? As population went up, economic output went up, and our use of fossil fuels increased in parallel. Coal drove the Industrial Revolution. That's why it happened in specific places in England, not randomly. It drove expansion in the United States. It drove railroads in the United States, and it made some people fabulously wealthy. Back when wealthy people put their money into libraries, unlike today. When we look at our use of coal and other fossil fuels, we went from 200 years ago, essentially we used wood, or we used animal dung. This is what we use now. It happened like that, blink of an eye, with respect to our entire 10,000 years-ish since we started developing city-states. Right now, 85% of all of our energy that we consume globally is a combination of coal, oil, and natural gas. 85%. Now, what's important is that is primary energy. A lot of people confuse primary and secondary energy. Secondary energy is, for example, electricity. Right? We generate and produce electricity by using fossil fuels and other resources. And it was people like Lavoisier who coined the term oxygen, then got beheaded during the French Revolution in 1794. We figured out these, what now seem to be relatively simple chemical reactions, where a fossil fuel contains carbon, in the case of coal, and there are bonds that hold one carbon atom together with other carbon atoms. In the case of natural gas, there are bonds that hold carbon and hydrogen together. And in the case of oils, there are an infinite number of individual hydrocarbons that are all held together by bonds. And we now know extremely well that the energy stored in those bonds, when we give it a little bit of a spark, it produces an exothermic reaction that yields energy. We feel that in the form of heat if you ignite a fossil fuel. Wood is a fossil fuel. And it also irreversibly produces carbon dioxide, water, and can result in methane leaking to the atmosphere. Now, it's relatively straightforward to go back over the last couple hundred years and calculate exactly how much coal, oil, and natural gas we as a society have consumed. And we can translate that into how much carbon we've put in the atmosphere. And if you watch, England lights up first. England is where intellectual patents, intellectual property could be patented by an act of parliament after the Glorious Revolution. So they started burning coal like nobody's business. That drove the slave trade. And then it diffused out across Europe to the United States. And today, we titrate into the atmosphere somewhere on the order of 35 to 40 billion tons of CO2 every single year. It's irreversible unless you employ something such as direct air capture to suck it out of the atmosphere. Right? And there's a lot of talk about that today. But this is not opinion. Right? These are relatively easy numbers to deduce. And if I sort of skip ahead, because you're all pretty smart and you get the point, look at what we've done. We have literally put a phenomenal amount of CO2 in the atmosphere. No doubt, right? Well, what has that done? Right? We can sum the total amount of coal, oil, and natural gas. It's easy to calculate how much carbon we've put in the atmosphere, and that's what I've done here in the red line. And as scientists, we can figure out what that does to the atmosphere. So in the late 1970s, early 1980s, there were some scientists working for Exxon. This is pre-Exxon Mobil. That was in the early 90s. And the scientists at Exxon, what they did is They looked at CO2 concentrations on the y-axis in 1960. They knew the concentration of CO2 in the atmosphere every year to 1980. They had those two end-member points, and every year in between, and they predicted that by 2020, the concentration of CO2 in the atmosphere would be 415 parts per million. Now, Exxon historically did not hire dummies. These are smart scientists. Some of them went to Michigan. Some of them probably went here to Arizona. They figured this out, right? It's really simple to determine this. And boom. Exactly what Exxon predicted. Exactly. The measured global atmospheric CO2 in 2020, 415 ppm. Right? Isn't it nice how science works? Doesn't have to vote. It's kind of like God said, yeah, that's a fact. Those same Exxon scientists, they also knew that those molecules of gases in the atmosphere, they wiggle, right? They vibrate. And when shortwave radiation comes in from the sun, gets absorbed on all the ground surfaces, it's then re-radiated as long-wave radiation, right? It's like a hula dance. All those atmospheric molecules start hula dancing because now they have more energy to absorb. So the scientists at Exxon said, hey, I bet you if we can predict the CO2 concentration as a function of time by extrapolating out how much each of the fossil fuels will be consumed, I bet you we could probably predict what the temperature of the atmosphere will be in the future. All right? So this is their data. This is an Exxon report. Y-axis is CO2. X-axis is time. They wrote the report in '82. Thank you to the Attorney General of New York. It's now available for all of us to look at. And then on the y-axis on the right side is temperature. So here was their prediction where you've got an envelope that includes their uncertainty. Now, I already said they were spot on with predicting CO2. And you can do really simple benchtop experiments to quantify as a function of how much CO2 in the atmosphere temperature will respond, right? It's like a dose response, kind of like a poison. Bam! I mean, right on. They predicted in 1982 that global atmospheric temperatures would be almost exactly 1 to 1.2 degrees C higher than they were in 1960, and that is exactly what the temperatures are. Isn't it nice how science works? And we see this when we look at the average anomaly temperature distribution globally, right? You see this, and what is it doing? It's getting hotter, right? The hula is moving to your right, just like Exxon predicted it would. Again, science is good, right? God, she was not dumb when she set it all up. So, what can we also use the Exxon, and now hundreds of other people around the world have replicated this. We can also predict the orange line here, which is if society globally continues to use coal, oil, and natural gas at the current rate and the forecasted rate, if we assume that countries in the global south attain the same lifestyle that all of us are accustomed to, it predicts that by 2100, global average temperatures will increase by 4 degrees C. And I'm pretty confident because the predictions from 1982 were literally spot on. I earlier said 85% of all the energy we consume is coal, oil, and natural gas. That 85% coal, oil, and natural gas is also responsible for 75% of the CO2 emissions. What does that mean? What does it mean for a world to be 4 degrees warmer? Right? Most adults can't think of how that would tangibly impact them. But I can. I'm a talker and a schmoozer, and I love talking to people in the most random places. When I drive around the country, I will strike up a conversation with everybody. And when, for example, I go out to Iowa, my daughter graduated from the University of Iowa, I now know several dozen corn farmers and wheat farmers and soybean farmers. I've driven through Georgia. I know peach farmers. Georgia's the peach state. Well, guess what? If the temperature of Georgia increases by 4 degrees C by 2100, there ain't no peaches growing there anymore. Because peaches, as all fruit do, require winter temperatures to be cold enough in order for the fruit to produce in the summer. If the temperatures increase by 4 degrees in Georgia, guess where peaches are going to be grown? Peaches are going to grow in Maine. So the peach crop is gone. And when you meet farmers in most of rural America, they're farming because their pappy farmed and their grandpappy farmed and their great-grandpappy farmed, right? It's part of who they are. So you can calculate the movement of different crop growth zones as a function of increasing CO2 concentrations and increasing temperature. These are the crop yields projected by 2099 to decrease. And I go back to this. Trust me. Did everybody see it? In the year 2100, in the continental United States, we will not be able to grow wheat. We will not be able to grow corn. We will not be able to grow soybeans. All of that will grow north in Canada. All of it. Georgia will not have peaches. Michigan will not have apples. Right? These are the tangible impacts that people feel. And I can promise you, when you talk to farmers, they'll tell you they've already seen this. Farmers in the Midwest are already seeing this. When the Wall Street Journal puts an article on the front cover that says the climate is changing in Iowa, you know damn Skippy the climate is changing in Iowa. They see this. They realize it. And then they ask, what are the solutions, Adam? And I tell them, I got a plan. So what's the plan? How do we keep temperatures from getting to 4 degrees warmer? Or how do we do it? How do we keep global temperatures from exceeding 2 degrees C relative to 1950? What do we do? Biden wants it. Almost all Republicans want it, except when they all get together in public and then they have a little shit fit that they want to say, oh, I don't want that. But in private, they all want it. Right? Because even Marco Rubio, he sees sunny day flooding in Florida. They're seeing the impact of hurricanes. People are realizing the decreasing crop yields, which cuts into tax revenues. Everybody seems to want this. They want temperatures to stay in the sweet spot. Right? And you read a lot from the Biden administration, the European Union, the Paris Accord. Everybody seems to want the same thing. The United Nations, all right, they came up with 17 sustainability goals. And number 7 is affordable and clean energy. 3 billion people on the planet right now lack access to reliable electricity. Now, what does that mean? It means that you can't refrigerate insulin, so diabetics don't have access to that. You can't refrigerate vaccines, so kids don't get vaccinated. These are the tangible things that result from people in the global south not having access to electricity. Right? It's real for them. One of my colleagues is from Sierra Leone, and his comment to me last summer when I visited him was, you know, Adam, you people in the developed world, you guys are worried about transitioning from internal combustion engines to electric vehicles. I'm worried about getting electricity. I'm worried about being able to take x-rays. I'm worried about being able to provide cancer treatments rather than people in Sierra Leone right now that just die. Right? There is no treatment. There is no modern hospital system. You hear about carbon neutrality, which means what? Means this. Means you have to electrify everything. Minus, and I'm not going to get into this, minus a little bit of nuclear. I'm okay with that. But you fundamentally have to electrify everything. Everything. Everywhere. So how do you do it? By 2050, if 90% of all of our primary energy comes from renewable energy resources, 90%, so we're basically swapping out coal, oil, and natural gas for renewables such as solar and wind. And I'll show you what it looks like. So this is my house, Ann Arbor, Michigan, 42 degrees north latitude. It's really fucking cold in the winter. We have 4 months of seasonal depression because it's gray and just disgusting. Okay? But this is my house. This is my backyard. Each of the solar panels was $190. They're 415 watts apiece. It's all DIY off the shelf with YouTube. If I can do it, and I'm not that smart, anybody can do this. Anybody. So I've got solar in the back. I've got an EV. This is my wife Alicia coming home at the end of the day, plugging in. I've got 6 lithium iron phosphate batteries, fully self-enclosed in the basement. And I can generate all the power I need. These are, in this photograph, these are mini splits, heating and cooling, 100% electric. You can take a house at my latitude and you can electrify everything. And I promise you it's better. You get induction cooking, way better. Everything is more efficient. And I promise you this, I'll plant the seed. For those of you in the audience who drive an internal combustion engine vehicle, the next time you go to a gas station and you hold that pump, you think about how disgusting humans are. We pick our noses in the car, we scratch our nether parts, and then we go and we touch that pump. What's on that pump? Right? That's the making of science experiments in 8th grade. It's nasty. I've never once had Alicia say, you know, Adam, I really wish I could stop at the gas station like I used to. It was so much fun. It doesn't happen. Alicia comes home and says, damn, this is nice. Right? It's also nice because, yes, my 50th birthday present to me was a Tesla Model Y, and I got to tell you, I'm addicted. I can wake up in my bed, it can be minus 10 degrees, I can take my phone out and I can preheat the seat and the steering wheel so that I can go out and sit down and it's like, woo, this is nice. Everybody can do it, and they're doing it. Mary Barra, GM, all electric. Volvo, all electric. The F-150, I've got a friend who drives one. My brother is an absolute southern redneck. He's chomping at the bit to get an F-150 because he's a contractor. And if you have an electric F-150 and you have every cordless power tool known to mankind, the end of the day, they're all in your truck, you drive home, you plug in, you go to sleep. That's it, you're done. All right? Cocktail hour can start at 4:30. You don't have to wait till 5 because you're not unloading the truck. All right? I mentioned renewable energy. I'll save the details for anybody that wants to talk about them. But if you calculate, and this has been modeled by people and fact check like nobody's belief. If you model how much energy, electricity we can produce with offshore wind, off the charts. If you model how much electricity we can produce by solar photovoltaic, off the charts. Right? Orders of magnitude more than we will ever need. Ever. Right? We've modeled this in Detroit. If anybody wants a great class project, I've done a class project where I teach students how to use GIS. And this is the land footprint for 10 million people. These little colored dots. 100%. Electrifying everything. It can happen. Right now, off the coast of Long Island, Equinor, used to be Norwegian Statoil, Equinor, in the Trump administration. They won the bid to build the first 1 gigawatt capacity offshore wind farm. I see the future with these up and down the coasts, just far enough that you have to squint, so people don't complain it blocks their view from Fire Island in the summertime, but just close enough that you can run copper underneath the water. So what does all of this require? This is where the geologist in me comes out. And I look at a Tesla and I see all the resources that have to be extracted from the earth to make all of these electric vehicles possible. All of our interior, even the vegan leather, right? Who knew? I wish I'd bought stock at $8 a share, but I didn't. I see all of the copper, the lithium, the nickel, the manganese, the cobalt. That's just in the battery pack. Just in the battery pack alone. All right? Then if you sum the total number of cars that are bought annually in the United States and globally, we need something on the order for 80 million electric vehicles globally, somewhere close to 7 million tons of copper per year, just for the vehicles. All right? If we look at how much copper we need for solar and for wind, the average offshore wind, you need about 10 tons of copper per one turbine. Onshore, about 4. And solar photovoltaic, this is on a per megawatt basis. Ask me about that later. So its capacity, about 5 tons. That's 86,200,000 tons of copper. That's a lot of copper. A lot of copper. Lot of copper. And there are lots more metals. Lots more metals that we need for each of these technologies to keep temperatures in the sweet spot. We got a problem. We've got a problem here if you look at this slide. So we are right now somewhere about here, bottom left. We know right now exactly how much copper mining companies around the world are extracting annually and making available for us to use. We know that. We also know, if we look at all the mines that will go into operation within the next 5-ish years, we know how much copper they'll produce. What do you see? You see by 2035, we're missing 10 million tons of copper. We're missing it. Now, why do we need that? We need that if all of us are using electricity from solar and wind and driving battery electric vehicles. Right now, we produce about 20 million tons of copper a year, which means by 2035, we have to continue producing 20, which you can see it's a declining curve, and we have to produce another 10. That's a problem, right? But humans are good at solving problems. The same thing holds for other battery metals, lithium. Look at how much of a supply deficit there is for lithium, how much of a supply deficit there is for cobalt. And the red and the yellow here, the red are Sustainable Development Goals, the United Nations, and the yellow are the stated policy scenarios by different countries around the world. Right? That's a problem. Because right now, the metals necessary to make our world renewable energy, we're not going to be able to provide them. Tesla, right? If Tesla wants to build 20 million cars a year, which I'm sure they would love to do, just look at the right-hand column, right? Tesla alone needs 165% of all the lithium the whole world produces right now. 165%. You can't do it. And it's true for every metal. So the y-axis here is supply divided by demand. How much supply mining companies supply and societal demand. A ratio less than 1 is not a good ratio. It's not. And every metal has a ratio less than 1 a decade out. Which means right now, we cannot, no matter what the people at COP want to do, can't do it. Can't do what Paris Accord wanted to do. You can't do what COP27 is going to say you want to do. None of it is possible right now. It just isn't possible because none of these metals are going to be supplied in the quantity that we need. So I grew up in North Carolina and I was taught like, oh, this is a problem. We got a problem. So what's the solution? Well, if you've seen the show Naked and Afraid, that ain't it. I've never met anybody who's willing to go naked and forage. Ever. Ever. So we take that off because that's not plausible. Right? I mean, honestly, who wants to come to class in here if it's dark? There's no lights, there's no air conditioning, everybody's buck naked. You know you don't. Right? So what's the solution? We have to significantly increase mining of metals. We have to. Now, we have to do it intelligently. We have to do it paying attention to environmental justice. We have to do it in cooperation with indigenous communities, with local communities and other stakeholders. It can't be willy-nilly just go out there and mine wherever you want. There has to be strategy employed. Right? We don't want to mine in areas where there are fragile water ecosystems. We shouldn't do that. But the only way to achieve renewable energy and keep temperatures in the sweet spot is we have to mine. So Mark, sitting here, I know has done a lot of work in Chile, and I've done a lot of work there as well. And Mark and I have both worked on this particular ore deposit called Candelaria. It's a deposit that produces a lot of copper. That's what makes this hole in the ground economic. If it didn't contain the copper, nobody would dig there. Nobody. So why does that hole exist? Because this is what you pull out of that hole. You pull out rock that looks like this, which is not the rock in my backyard. And I know I'm in Tucson, so some of you might have rock like this in your backyard, but it's not normal, right? So that's why this hole exists. One hole in one place, and it's somewhere where indigenous communities are concerned about environmental justice. So what are the challenges? Among them, this is a graphic where from left to right, you're looking at how deep ore deposits are that we mine. And what we know is we're having to go deeper and deeper and deeper in Earth's crust to find new metals. It takes a long time to get a permit to mine. On average in the United States, it's more than a decade if you can get a permit, right? I mean, come drive with me sometimes, and I love it when I pull behind a Subaru, which for me is just the epitome of the ultra-liberal anti-miner. And the back has bumper stickers, anti-mining, I don't want mining. And my kids get frustrated with me because I actually have engaged in conversation with people driving those vehicles, and right away they're like, son of a bitch, don't point it out to me. But we have to, right? The other big problem is the average length of time from when someone finds a special volume of Earth's crust that contains a really high concentration of one of these metals we need. From the time they discover that to the time that a company has built all of the infrastructure and makes that metal available is on average greater than 10 years. So let's go backwards. We know right now we're on a course to hit 4 degrees C by 2100. That's bad. Nobody wants to hit that. We know how we can avoid that, which is to build almost like a Marshall Plan effort to build renewable energy and battery electric vehicles. We know exactly how much lithium, cobalt, copper, nickel, zinc, cadmium, etc. we need to build all of that infrastructure. And geologists are pretty good at finding that. But when we talk about 2030, 2035, right, if one of Mark's graduate students finds a new deposit in 2025, it's going to be 2036 before it's producing if they can get it permitted. The other challenge, and I'll just highlight this, if you look at this negative cash flow, mining is really, really expensive. Mining companies take on phenomenal debt, sunk costs, 5 years, 10 years, 15 years, 20 years before they ever break even. So companies only want to engage in exploration and mining when they know there's the likelihood or the certainty that they're going to get permitted. So back to this hole in the wall, and I've got one slide. Just for electric vehicles alone, we need 8 Candelarias every single year until the entire world is driving battery electric vehicles. This is not wind turbines. It's not solar photovoltaic. It's only battery electric vehicles. And right now, we're not finding 8 Candelarias every single year. Because when we look at the academic climate, academia in the EU and broadly in the United States has lost its appetite for mining geology. We had a significant increase in the number of people studying climate change. I think that's great. But we get it. We don't need more. Let's pivot. What we really need now is we need to double down and we need to start training more geologists to find the resources that we need to mitigate climate change. And I don't mean to disparage people who are interested in studying climate change, but honestly, we don't need to know the temperature to the 5th decimal place. Who the fuck cares other than the one person and the people they went to grad school with that they see at one meeting a year? Nobody cares. Like, I shouldn't be breaking this to anybody. Nobody cares except for you and 5 other people. That's it. So we have to radically change our mindset around mining, right? And I know when I say this, I can read body language and there's cringing. Oh, I don't like that. But trust me, you want everything that is made available by mining. And then what we need to do is once we get to a 100% renewable energy infrastructure, we need to, from here to there, make sure that engineering programs are hiring, well, they're not, I guess on some level, they're almost, yeah, you pay to go to school, right? We need to increase recycling of these metals to 100%. Right now, globally, we recycle less than half the copper that we mine. It gets landfilled. So we need to evolve towards this circular economy where once we have achieved an infrastructure that is entirely renewable, then we can put the brakes on mining. Because renewable energy and all the products we use takes less electricity. Right? Why do you have the little thingamajiggy when you plug your iPhone in? Because it's stepping the voltage down. It doesn't need 120 volts. So everything becomes more efficient, and ultimately you need less. So this is my last slide. We're stuck. Right now, cognitive dissonance has us stuck. We elected President Biden, who was going to get rid of oil until he went to Saudi Arabia and said, please, please, please pump more. Right? We had the Trump administration give the permit to Equinor for the wind farm. We're stuck because we, in essence, have a large coalition of people in society for whom, and I read them all, for whom the New York Times is your holy Bible. And the New York Times, their front page is lithium mining in Nevada is bad. Cobalt mining in the DRC is bad. Okay, then where do we do it? We have to do it, so where do we do it? We don't want to mine Thacker Pass? Well, that's great. But I've been all over Chile, and I can tell you people down there are looking at us like, no, we don't want you down here anymore taking our resources. Get your own. So where do we do it? I really think that as a society, we all have to sit down and say, okay, we know from these Exxon scientists, we know exactly what our trajectory is now. We know. It's not rocket science, right? We know how we can eliminate that. We know. We know what we need for that solution. We know. But what we have now is we have, and I'm dividing in half, we have we have the left who are just all out anti-mining. No mining anywhere, anytime, right? It's not even NIMBY anymore. It's banana. Build absolutely nothing near anyone. It's banana. And they're eating bananas that are brought here on fucking ships that are air conditioning from Central America. Is that me? Then we have everybody on the right. And who's on the right on average are financial firms. Who has the capital to finance all the exploration? Most of that is on the right. But they don't have certainty of whether or not their investment is going to generate a return because of everyone on the left that's fighting mining. And as I said, there are some places we shouldn't mine. Maybe the boundary waters in northern Minnesota. But the Duluth complex has 90% of the cobalt we would need to electrify everything. 90%. You eliminate child labor in the DRC, but nope, nobody in Minnesota wants to mine. You go to Wisconsin, if you look at the Wisconsin state flag, there is literally a shovel and a pickaxe. You know why? Because European white people colonized Wisconsin to mine. And 6 generations later, nobody wants to mine. But they love all of the benefits of mining. So what we need to do is we need to have, and I'm right in the middle, I'm a switch hitter. We need to have the left and the right all agree that we want temperatures to stay in that sweet spot, where Greenland doesn't melt, Antarctica doesn't melt. We have fewer sunny day flooding events in southern Florida. We have fewer 100-plus degrees in Los Angeles. All 6 million people in Phoenix who have allergies to plants because they idiotically brought them from the Northeast when they moved to Phoenix and air condition and humidify them, they can all have their air conditioning. We have to do it. We have to do it for the 3 billion people on the planet who don't have access to reliable electricity. 1 billion people on the planet have no electricity. I go to West Africa every summer, and when I was in Liberia this summer for 10 days, there's nothing. There's no electricity unless you have the ability to afford a generator. That's it. They don't have what we take for granted. So we have to move beyond these positions that we've chosen. I'm anti-mining. Really? Because I'll be in West Africa next year, the first week of August, and I'd love to take you with me. And I'll have you explain to the people who are there who want renewable energy why you're going to disallow them from having it. Right? Let's go. I'll pay. 100% guaranteed. I've made this offer for 10 years. I've never had a student take me up on it, except the students who did. And when they went and they saw energy through the eyes of people in West Africa, everything changed. Everything changed. It gave them perspective that nobody has growing up in the U.S. Even me, I grew up dirt poor on welfare with free lunch. I know what the taste of welfare cheese is. It ain't good. But I still grew up with so much more than half of our global population. So if you're someone for whom energy justice, environmental justice, that is your tingling sensation, let's do it together. We have the solutions. We have to change our mindset, or we're screwed. Thank you.
All right. Thank you, Adam, for the talk. Now it's time for questions.
Fire away.
I think we can go first with students. Yeah, okay.
Okay, Adam, great talk, by the way. That was awesome. So why not like nuclear short term to buy us time to better our recycling and get these materials, get these policies changed?
I'm a big fan of nuclear. And right now, I'm watching every press report that's coming out of Terra West, which is a company backed by Bill Gates Foundation, in southwestern Wyoming, ironically, in a town called Kemmerer, that was colonized by white people to mine coal and put on the Pacific Railway. Coal went bust, the town went bust. They're now spending, I think it's $4 billion, $2 billion DOE, $2 billion from private capital, Bill Gates mostly, to develop a new modular reactor that in essence is the same type of technology we developed in the 50s for submarines. Small modular reactors that allow submarines to run silent and run deep. I think they offer a lot of potential for baseload power. And for those of you who don't know what that means, if you think of 100 units of electricity that you consume in a day, baseload is what is consumed at all times, even when we're all asleep. There's always some amount of vampire electricity that we're consuming all the time. So I think nuclear power could be used. Modular reactors that I tell my students, when I envision them, they're on the back of my electric F-150. Which, by the way, I got a friend who just bought one. It is an amazing, amazing vehicle. And he did take a road trip from Ann Arbor to Boulder. Everybody always says, I can't have an EV. What about my road trips? And then you ask them when the last time they took a road trip, and they'll tell you it was a movie that they watched. Anyway, so I'm a fan of nuclear. But remember that nuclear reactors, you can't dial up and down. Right? So if you have a nuclear reactor and it is inside the reactor, you've got uranium-235 atoms are spontaneously undergoing fission and releasing energy. One uranium-235, one atom, when it becomes uranium-236 and then immediately experiences fission to barium and krypton, releases 202.5 million electron volts. Right? So on an energy density basis, that's why I'm a proponent of nuclear. For baseload power, and then you use wind and solar and batteries for meeting demand during the day.
Cool. Thank you.
Any other question? Yep, coming.
So you just you just went real quick on the part when, so you're basically saying to produce more metal, but you went real quick on the part when you just said we need to recycle those metals.
Yep.
So if this is not possible, then what, like, we're not sure that this is possible. It's not possible to recycle 100% of metal. So if this is not possible, what's the plan?
So recycling is possible. Right now, the metals that we recycle are those for which it makes economic sense. So it's economically sensible to recycle steel, to recycle copper, if you can pull it out of whatever technology it's in. When we look at most of the metals in our laptops, in our smartphones, in our new LED TV screens, a big challenge is it's cheaper for a certain country that has a red flag in Central Eastern Asia to produce those because human capital is much cheaper there than it is elsewhere. And so they're able to essentially produce those metals at a lower price than what we could than it would cost to recycle them right now. So companies aren't doing it, but they're starting. So Apple has already been, for the last 10 years, they have invested in a remote battery-operated system that their goal is to be able to extract every metal that's in an Apple product. That's what I mean by that circular economy. So when an Apple product reaches its end of life, Apple will then recycle all of that. And that is, for them, a really smart financial decision because that reduces the amount of new virgin metal they have to buy on the open market. So we're getting there. And that's what I mean by in parallel. You know, over the next couple of decades, what we need to see a rapid advancement and deployment of renewable energy resources. Battery electric vehicles will drive fewer vehicles, right? I've got 4 kids, and my 18, 20-year-old, they don't have a car. They live in Boston and Manhattan. They don't want a car. Car insurance is expensive. They don't need a car, right? In New York City, they have Tesla Model Ys by a company called Revel. They're awesome. Go on the app, you use it when you want to drive it. So it's an all of the above solution. I don't know if that answered your question.
Yeah, but you definitely need a car if you live in Tucson, though.
Yeah.
But thank you, got it. Thank you.
Hey, Adam, do you know the Pebble Mine in Alaska they're trying
I do.
Can you make an argument for and also an argument against it, and then what your opinion is on it lastly?
So for those of you who aren't aware, there is a volume of earth in south central Alaska, and it's called the Pebble Prospect. And over the last 40-ish years, they have drilled about, I think, 1.5 million feet of drill core. And if it were put into production as an open pit mine, it would be, on copper alone, I think the number 8 or 9 producer in the world. When you sum the amount of copper, gold, silver, molybdenum, and some other metals, it would be the number 1 mine in the world for all of those metals. It would produce enough copper for the United States to go 100% renewable, that mine alone. The problem is that that volume of earth is uphill from one of the world's most pristine salmon fisheries. And there's a saying in the news, if it bleeds, it leads. If it bleeds, it leads. Thought I got that right. So people are really concerned because if you build a mine upstream of this pristine salmon fishery, you also have to store all of the excess rock that you dynamite and bring out, and we call that, tailings or waste. And that involves both solid material and also big tailings ponds that typically become enriched in toxic heavy metals. And the concern is that if that mine tailings pond were to fail, all of that waste would flow down into, it's not Bristol Bay, I'm blanking on the name of the bay, and would wreak havoc on the salmon fisheries. Indigenous communities in that area remember extremely well the Exxon Valdez, right, which was a horrific nightmare where a massive oil tanker hit an offshore reef and spilled millions upon millions of barrels of oil into what was then pristine fishing grounds. So it's hard for me to say yes or no. I would propose, and again it comes down to economics, they need to build a new rail system and road to get all of the equipment in and to get the ore concentrate out. I've never looked at economically, could you actually take all of the waste and move it somewhere that is not upstream from the salmon fishery? The answer is yes, you could, but what would the cost be? And the reason that's significant is, on average, when you dig a hole in the ground because there's, 1%, 2%, or 3% of that volume of earth is copper, the other 99% is waste rock. Right? So 99% of what you excavate, you have to store somewhere. I haven't seen anybody actually float that idea, but I would venture to say if the Biden administration really wanted to make a move, they would figure out, working with the mining company, and I'm blanking, some Anglo pulled out, right? Do you remember if anybody else has bought in? I don't think they have. But it's basically been $1 billion of sunk capital over 40 years. If the Biden administration were to step in and say, look, how do we solve this problem? How do we preserve and effectively eliminate any possibility that the salmon fishery is ever impacted? They could do it. And that's what I mean. That's part of what I would say is like the Marshall Plan, right? I mean, think of Germany after World War II, right? I mean, it was like somebody flushed a toilet. And then we had the Marshall Plan, and look at Germany now. And that happened really quickly. So it can be done. It just takes people who can move in that direction. What I've seen the Biden administration do is they have hired some really smart people who focus on indigenous rights, indigenous communities through the lens of indigenous communities, environmental justice, but I haven't seen them bring in any intellectual firepower for how do we actually get this done. There's a lot of this that's happening, and they're not solving the problem.
Thank you.
It's a long answer to your question, but
That's great. Yeah, thank you.
Is there any other questions?
This is it's kind of a naive question, but how much of this metal is there? Are these metals are there in the world? Of course, it's not infinite, but I'm trying to understand, like, even if we could do this completely well, like how long does this take us? Because I think you showed a graph